This is our preparation, nuclear waste, and then you had some reading. And we had this Excel coding cost of nuclear electricity. Okay, so what I'm going to do today is I'm going to go through and explain some of the concepts in the videos and the reading, and I'm going to take you through the Excel coding assignment, and you can finish it tonight. Okay?
Okay.
So this is your first question. All right? We enrich uranium. What does that mean? How do we enrich uranium? What is the process? This is a test. Ready? 3 choices.
Yeah.
Okay. I want you all to answer. And then I'm going to put you in your breakout room and you'll talk about it with each other. And if there's a problem with it, I'll visit and you can tell me what the problem is. Okay? All right. Welcome back. I visited some rooms and it was great. You guys were arguing about this. I love it. Right? So now what I've done is I've increased the choices. Right? And let's go back to the choices here. Wait, I have to share my screen. I have to remember to share the screen, Pete. Here we go. No. There it is. Okay. Hey, mute yourself now, please. Yeah. Okay. So there are those 3 choices. 4 is none are correct, and 5 is they are all part of the process. We need all of them. So which one through 5 is right? Read them and think about it. And then all 18 of you are going to vote. Even if you're wrong, it's okay. No one's in trouble. There we go. Please pick the correct answer. I've got 7 people, 8 people, 10 people have answered. We've got 6 more. Come on, pick your choice.
I can't see the voting. The voting process is not popping up on my.
Can you reactivate the options?
No, stop. Here are the results. Can you see the results right now, Victor?
Yeah.
Yeah. Okay. Okay. So look. Now, I think you all did a great job because I'll tell you. So if we look at this, before you started talking, a whole bunch of people were saying 1, that we turn 238 into 235 by pulling off neutrons, right? I want to explain how wrong number 1 is. Okay, what you're saying is we start with U-238 and we pull off 3 neutrons and leave us with U-235. You can't do that. What you're saying is you have a nucleus and you pull out 3 neutrons. You can't do that. Right? You can't mess with it. What we're doing is we start with 238 plus U235, and we know this is only 0.7%. This is 99%, right? What we're trying to do is separate them, okay? So that's a myth, right? However you learn that, you cannot turn. Now, you could turn U-238 to U-239. How would you do that? Right? You would do that by adding a neutron, right? And does that ever happen? It does in a nuclear reactor. That's how 238 turns to 239, turns to plutonium, right? But you can't make a neutron come out. They're in the nucleus, okay? So that's a really important thing. Two is the right answer. We're just separating them, okay? And so how much do we have to separate them? Well, to be in a nuclear reactor, we need like 3 to 5%. Weapons grade, it has to be very pure. Now, you probably looked through, there's a whole bunch of different ways to try to separate them. I'm just going to talk about two of them using a centrifuge and membrane diffusion. We have to use the difference in their masses. How different are they? Are they very different in mass? Only by a
Yes,
little
they
bit,
are.
right? Only by a little bit, about 1% difference. So how can you do that? You know, what you could do is you can imagine if you put them in a tube. Okay, so first of all, sorry, all the methods I know about require it to become a gas, right? And uranium is a solid metal. So you get to 230, or you get the uranium and you put 6 fluorides on it. And it doesn't increase the mass very much because fluoride is very small, it's very light compared to uranium. Okay. And so this is a gas at just relatively warm temperature at 56 Celsius. And so what you could do, you can imagine if you had a big tube and you put this in, there would be more of the 238 down here and more of the 235 up here. And then you could separate them. But their difference in mass is very little, and this wouldn't work very well. So if you spun it, if you could increase gravity, it would work better. And so they spin them very, very fast in this ultracentrifuge. And so if we look at this thing is spinning around. This cylinder is spinning around very, very fast. Okay? And so what happens then? The larger, the heavier nuclei are preferentially pushed to the outside. And the lighter nuclei they come into the middle more, right? So what happens is you feed in the mix of both of them. And on the outside here, you have more 238. And on the inside, you have more 235. Okay? And then this lighter stuff will come to the top and circulate around. So you get this circulation. And you draw the 238 out the bottom and get rid of it. The 235 comes out the top. Comes out the top like this. And this is your enriched stuff. Okay? This is how they're trying to do it now, or how they do it now. And so when we talk about a lot of the free world is concerned about Iran highly enriching uranium for a bomb. And this is how they're doing it. And one of the methods that they're using to try to stop them is if they can break their ultracentrifuges, right? But it's hard because they're in Iran, right? Now, there's another way, and that's membrane diffusion. That's the way the United States did it during the Manhattan Project. That's what happened at Oak Ridge, Tennessee, where they purified uranium-235. And what that relies on is the fact that the lighter molecules are going to travel faster. Okay? So you folks are somewhat technical, right? You've probably learned. Have you learned the equipartition theorem? Do you know what that means? Do you? No, you don't. Okay. With the equipartition, can you see this? Equipartition. I think that's right, small p. That means when you put things in thermal equilibrium, right, a whole bunch of molecules, on average, they have the same kinetic energy, all right? And so kinetic energy, you can see, is 1/2 mv squared, right? And if a whole bunch of objects have the same kinetic energy, the ones that have greater mass must have smaller velocity, okay? So if you put like uranium gas in with oxygen, the oxygen is moving around very fast, and the uranium, those big fat guys, they're going very slowly, right? So membrane diffusion makes use of that, okay? Now, if we solve for this, right, we can say V is equal to what? Energy times 2 over the mass square root, right? Okay, now where does that 3 come from? Oh, I'm sorry. And energy we know is proportional to temperature, right? And you can use the Boltzmann factor, KT, or you can say we're using molar and use the gas constant, RT, okay? So on average, the molecules share this equally, right? Where does the 3 come from? The 3 comes from the fact that this is energy shared in the X component, the Y component, and the Z component. That's where that comes from. Okay, so what we know then is that uranium-235 molecules are traveling faster than the 238 molecules. Are they traveling a lot faster? Or just a little faster?
A little faster.
Just a tiny bit faster, right? Because if they have the same energy, the masses are only different by 1%, right? And actually, when you take the square root of a small number, it's even smaller. And so it's actually about 0.5% difference, right? They travel almost the exact same speed, but 235 on average is going to be a little bit faster. And so how this works is they have a membrane. So you feed the gas in here under pressure, and there's little holes just big enough for the molecules to get through, and you push it out, right? Now, the ones that are moving faster, 0.5% faster, they are going to hit the holes at a higher frequency. And so they will preferentially diffuse through these holes. Now, both of them diffuse, right? But these go through a little bit faster. And so when you come out, you have this gas has a little bit more U-238, and this gas has a little bit more 235. And so we look at both of these processes. So this is how we purified uranium-235 to make the first hydrogen bomb that we dropped on Hiroshima. I mean, I wasn't there. I can say the United States, though. Now, you can see from this process, we're not going to make them very pure by this method, only a tiny bit more pure. As well, with this centrifuge, this gas coming out is only a little less pure than this gas coming out. Only a tiny bit. So what do? If we want it real pure, you have to do this again and again. So we take the enriched stream and we purify it again. And we take this enriched stream and we do it again. And so you have these processes where you put in the feedstock, and this is more pure up here, and this is less pure, and then you run it through the next one. The less pure goes down through here again, the more pure goes to the next one. You do this over and over and over again, and you end up with something that's very pure if you do it long enough. It takes a long time, and it's a lot of money. So then you ask yourself, what do you do with all the other stuff? Right? Because only 0.7% of it is 235. So you get a whole bunch of 238. And this is called depleted uranium, DU, depleted uranium. And so, you can store it. It's really heavy. And so they use it for the tips of armor-piercing bullets. It's worth noting that in the Iraq War, the United States, I don't know how much, but tons of uranium was used in the armor-piercing bullets. And there's a huge amount of depleted uranium all over Iraq. That's bad. It's not fissile, but it's still radioactive and it's poisonous, right? So this is one of the artifacts. So there goes that's enrichment. We're done with that part of the class. So we understand enrichment, you can't pull neutrons out of a nucleus. Enrichment is just about separating the molecules. And you can't do it chemically. You can do it if it was plutonium. That's chemically different. You can't do it chemically to separate one uranium from the other. You have to use a difference in mass, and the difference is very small. So it's very hard, but you can do it. All right. In mining uranium, I thought this is worthwhile, especially for Malawi, because we mine uranium in Malawi, right? And there's a question like, well, if we're going to mine it, shouldn't we refine it too? So then we can get the money from the refining process. Might be a good idea, providing a lot of employment for people. But you have to be very careful because uranium, is dangerous. I'm adding these. I think I gave you an article to read. Compared to burning fossil fuels, mining uranium and disposing waste is very safe comparison, but it's not perfectly safe. And the people that suffer are the poor, right? The people living in the areas where uranium is mined. In particular, it's the Native Americans. So they're very poor. They live on the reservations, and the United States has gone in and mined that uranium, and it's polluted the groundwater. A lot of people have died. So it's not perfect. Or maybe it would be better to say that the powers that be are not very concerned about the poor people. And I think that is a universal truth that we always want to accept, because Malawi is poor people. And so we can't rely on the global powers to give our health here in Malawi a high priority. We have to take care of ourselves. All right, so disposal. Look, this is all very just historical. This doesn't matter anymore because we're not going to use a large repository. Okay. We are going, it seems right now, we're just going to keep, in the United States, we're going to keep the nuclear waste on the site and just leave it there forever. In France, they might reprocess it and use the plutonium again, right? But anyway, for a while, we were talking about Yucca Mountain and the amount of work that went in to making sure this would be perfectly safe out in the middle where nobody lives. There's hardly any rain. And they were going to build these big tunnels underground to put in the nuclear waste. Now, there's a problem here that they don't talk about. How do you get the nuclear waste from the nuclear reactor to Yucca Mountain? Right? That's hard because you can't kill people along the way. We don't want to do that. You'd have to put them in trucks or in trains. What if that truck had an accident? Right? So all of those things are problematic. And I'm a very strong proponent for just leaving the nuclear waste where it is at the facility. But so they went through this, they did a whole bunch of calculations, spent billions of dollars just planning this. And then Barack Obama ultimately said, look, this isn't going to work, forget it, right? And they canceled it. But let's take a look. This is the radioactivity as a function of time. So this is very important from a perspective of nuclear waste or radioactivity, is we showed that initial slide where a neutron hits 235 and it splits into two daughter nuclei or three. And there's a whole bunch of different radioactive products that are given off, and they have all different half-lives, right? So we take a look at this, for instance. This has a very short half-life. Foomp, it's gone in only like a day. And then there's some things that have very long half-lives, like this substance here. It takes many years to get rid of. Or, yeah, some of these longer half-lives. And so if you look at this curve, this is a total radioactivity over time. And what you can see is when it comes right out of the nuclear reactor, you have radioactivity is over 1 billion, okay? And in one day, it drops by a factor of 10, right? Which is huge, right? If you wait a year, it drops by a factor of 100. If you wait 100 years, it drops by a factor of 1,000. And this is because the really radioactive stuff has a short half-life. It's exploding really fast, and then it's gone. The stuff that has a really long half-life, like this stuff, right? That's not really radioactive. So it's down lower on the scale. And so consequently, and I remind you, I said this about Fukushima, that when they had the meltdown, they said, just keep it cool a little bit longer because tomorrow it will be less radioactive, right? And so you look at this, nuclear waste isn't a problem if we can confine it for a long time. And then you look at, well, how long can we confine it? And so these are your codes. This is computer modeling that they said, how long will the packaging last? Like if we put it in these big concrete canisters, we can tell you that, nothing is going to break in 100 years, right? It'll be good for 100 years. In 1,000 years, there's one chance in a million, right? Or one chance in 10,000. Now, in 1,000,000 years, we can bet that they will all break open in 1,000,000 years. But then you go back and you say, well, in 1,000,000 years, it's not radioactive anymore, right? And so when you combine this reduction in radioactivity with the quality of the container, you get a curve that looks like this. This is the amount of radioactivity our computer models would predict. All the different substances. And so you see no radioactivity in the beginning because the canisters, they work. And the radioactivity at the end, after a million years, is low because it's no longer that radioactive. Okay, and so I just want the last concept is how ridiculous this concern is. This is the amount of radioactivity that we allow, that someone has allowed, the government. And they said, okay, well, we won't get up to that level for well over 10,000 years, about 100,000 years. And then the EPA, the government said, no, that's not long enough. It has to be good for 1,000,000 years. And I just want you that to sit in, that climate change will likely destroy us in the next decade or 100 years. And you have these scientists and politicians arguing about if container storage will be safe for 1,000,000 years. Like, no, this is a waste of time. Okay. So the short answer here is nuclear waste is not a problem. It's a concern. We have to take care of it. But it's not like climate change. That is a problem. It's destroying the world. Maybe an overstatement. Sorry. Let's look at cost. So in theory, nuclear energy should be cheap, but in practice, it's not. And we have this isn't a simulation. These are all of the nuclear reactors in the United States. Oh, no, in the world. Sorry, in the world. And they calculated the cost of the nuclear energy. Here is Diablo Canyon. This is the one near my house, and it's pretty expensive. You know why it's expensive? They started to build it backwards. How that happened, I don't know. But they built it so that the heat repository was on the uphill side, so they couldn't run the seawater in, and they had to go back and redesign it. And so the thing that costs nuclear energy so much is because you have to custom design it in order to work in its location. And you don't have to. It's just that's the way it's always done. And so that's the key to making it cheaper. All right. So I'm going to skip. Let's see. You have construction costs. No, I'm not going to talk about this right now. Okay. Sorry. Right. I just wanted to distill the ideas down. The cost of nuclear is dominated by the huge amount of capital cost of building it in the first place, right? A solar farm, so maybe you know, solar panels are getting cheaper and cheaper and cheaper. And now you can buy solar panels for less than 10 cents a watt in Malawi. They're imported, actually, one of our technicians imports them, Samuel. So 10 cents a watt, that means you want a 100-watt panel, that's only $10, which is approximately 30,000 kwacha, right? In comparison, the capital cost for nuclear is $5 to $10 a watt. So 10 times as much. And so when you build a nuclear reactor, all the money comes up front and you're in debt. Okay? And you need to make money. The problem is you can't make money right away because they take 10 years to build. They take 10 years to build because it's a long process, because you have to custom design them, and because you have all of these problems. You have protesters saying, no nuclear, stop it. You also have regulations saying, how do we make this safe? And so it's a lot of paperwork. It takes a long time. What happens in that time? Well, you just took out a lot of money and you're in debt. And that debt increases because of interest rates. Okay? So the construction and the placement of a nuclear facility is where all the expense is. It's not about the fuel. The fuel is relatively free, costs very little. And so how do we address that? In order to make it cheaper, you'd want them to be modular. Like you want a factory pumping out nuclear reactors and sending them off into the world, and then people just applying them. That's how we make desks inexpensive. That's how we make everything else, right? How can you reduce the how can you reduce the construction time? Same answer. Make them modular. So, oh, you want a nuclear reactor? Boom, I'm going to produce one, send it off to you tomorrow, right? So that's the solution. We'll talk about that tomorrow's class of how are we improving nuclear over the time. So in summary, nuclear is beautiful, it's safe, carbon-free compared to coal, which is the very worst. Radioactive waste, it's a problem you have to deal with, but not a big problem if you're careful. You damage the environment when you enrich or when you dispose of depleted uranium, but that's nothing compared to coal. One, the carbon dioxide. Two, the particulate matter in the air that causes pollution. And three, that causes cancer. And three, the ash after you burn the coal is mountains of it. And they've had problems where dams, where ponds of this stuff flow into communities and poison people. Okay. So nuclear is so safe and clean compared to coal. And yet humanity is being very stupid because we're still burning coal. How much? Well, here we go. This is the amount of electricity produced over the years from 1985 to last year. And we see coal is still growing and nuclear is not increasing very much. It's remaining relatively constant. Let's take a look at percentage-wise, right? Whoops. No, there we go. Percentage-wise, coal is still king, 35%. Now it's coming down a little bit, mostly because of the growth of renewable energy. Nuclear is not increasing. There's only one country where it's increasing, and that is China, right? I think I showed that. Yeah, I showed that yesterday. Okay. All right. So I'm adding to our summary. Coal is still the greatest share of the electricity market. Boo! We won't run out of nuclear fuel, but nuclear is expensive. It's dominated by the capital cost. And this is something else, is that the energy landscape, well, nuclear requires a 50-year commitment. If you say we're going to build a nuclear plant, you've got 10 years committed to building it, and then you've invested all your money. You're going to use it for at least 40 years. And after 40 years are over, you're going to say, no, please, 10 more years, because it's already working. That's what's happening at Diablo. They were supposed to close Diablo, and we're like, no, we already built it, right? It's producing free electricity now because we've already paid it off, right? So this is something other people don't talk about. The energy landscape changes very fast, right? Solar is decreasing. Batteries are decreasing very quickly. Like every 2 years, it gets cut in half. Electric cars are growing. Artificial intelligence is gobbling up electricity. Everything is changing at a very fast rate. We don't even know 50 years from now, are we going to really want to have a grid? Or are we just going to have small localized generation? Do you want to commit for 50 years to a technology for producing electricity? Now, that's just a question. I don't want to. You might think it's a fine idea. But that is something to consider. If we want to go nuclear, we're going to be nuclear for 50 years. Okay? So what I'm going to do now is I'm going to send you to your breakout rooms, and you're going to talk about the questions that you might have. I'll visit your breakout rooms, and then I'll try to answer the questions. After that, we'll talk about the financial model, the Excel sheet. Okay? All right, everybody, welcome back. The only question I got was, is uranium hexafluoride dangerous? My answer is yes, it's very dangerous. I'll look at the details, but fluorine itself is horribly poisonous. And please mute yourself, James, Glory. Yeah, it's horribly poisonous, and uranium is poisonous. But what I found when I visited breakout rooms is you were not talking about your questions. Everyone was talking about, should we have nuclear in Malawi, right? That's not what you were supposed to talk about, but I'm really glad you were, because that's what this class is about. And we will dedicate Friday's discussion to, what about Malawi? What are we going to do? Should we use nuclear? Okay. So let me just take a couple minutes and show you the Excel spreadsheet. Okay. Here it is. All right. And so what we see here is this is a computer model of your bank account, right? You take out a loan for $7 billion, for $1 billion to build your nuclear reactor. Okay. Oh, no, this isn't a nuclear reactor. Pardon me. This is a natural gas combined cycle reactor, right? So you take out your loan. I was going to say you can't build a nuclear reactor for $1 billion. It costs $10 a watt. You need a gigawatt. You need $10 billion, right? And so what you see, you go into debt, right? You start out. So this is your bank account. You have negative money in the beginning, but you start gaining money by getting revenue from selling electricity. And you can see that if you just raise the price of electricity, let's say you raise it to 25 cents, right? All of a sudden now we're not in debt very long. We make way more money. But you can't do that because 25 cents a kilowatt hour, pardon me, is too expensive, and you will lose because other companies will replace you. How about if you just charge 10 cents a watt? Pardon me, 10 cents a kilowatt hour. Oh no, we just go deeper and deeper into debt. We will go bankrupt. And so you have to find the right price, maybe 15 cents per kilowatt hour. And you're like, well, no, we're not quite as deep into debt. How about 16 cents per kilowatt hour? That's a little better. How about 17 cents a kilowatt hour? And you're like, oh, okay, it will take us 30 years to pay off the loan. And after that, we'll have a lot more money. Now, what if instead of producing electricity at 25% duty cycle, 1/4 of the time, we are able to produce it 75% of the time? Now we find that we're not in debt very long at all because we're making more money faster. And now we could probably charge 15 cents. We could probably charge 12 cents. Yeah, we could charge 10 cents. Yes, we could sell our electricity very cheap. Okay. But now we want to build a nuclear reactor, right? So now instead of $2 a watt, we need $10 a watt. Oh, crap, man. Now we're in debt. Okay. But fuel is really, really cheap, right? So we don't have to pay much for fuel. Yeah, it's about 1 cent a kilowatt hour. 0.01. That helps a little, but not a lot. And now we have to charge more for electricity. How about 20 cents a kilowatt hour? But for a nuclear reactor, we're going to run that, 95% of the time, right? Because we only turn it off when we change fuel rods. It's running all the time. And you're like, okay, this is pretty good, 20 cents. it's more expensive than the natural gas. And there are a bunch of other things we can change. Oh, yeah. What if the interest rate is only 7%? Whoops, sorry about that. I made a mistake here. Yeah. Then it works better for us because we don't have to pay off the loan as much. Isaac, you have a question.
Yeah. Yes. I think I tried to go through it yesterday, the Excel, but I think I was not understanding some parameters, like maybe the duty cycle, the
Yeah.
duty cycle. Can you just come on it, and how does it affect the results on the graph?
Yeah. So, okay. So do you know what duty cycle means? Do you know what duty cycle means, Victor? It's the percentage of time you are running electricity and selling the electricity, right? So we look at the amount of electricity you generate. Double click on this, right? It's the duty cycle times the number of hours in a year times the size of your reactor. Okay. Now, this is 500 megawatts. Let's say we want to have a gigawatt facility, right? So we can change it to larger, and now we're generating more electricity. So that's where duty cycle comes in. That's very important because if you have a small duty cycle, then you have this capital cost that you've paid, and you're not making any money. So you're going to have to increase the price of your electricity. So if you have a small duty cycle, you have to charge a lot of money for that electricity. Now, your efficiency is, that determines how much fuel you have to use. So your fuel costs, where's fuel cost here? Operating costs, right? The efficiency comes into play because if you're not efficient, you have to buy more fuel. And so the total operating cost is, let's see, F3 is your maintenance to keep the place running, plus operations. We'll get back to operations. Operation times B6, which is the amount of money that you put up to build it in the first place, plus D3, which is the amount of fuel that you have to pay, right? The amount of fuel times the amount of electricity you're generating, because if you generate twice the fuel, you're going to need twice the amount. If you generate twice the electricity, you're going to need twice the amount of fuel, right? And you divide by efficiency, because if the efficiency is low, you have to buy more. You have to buy more fuel. So all this comes into play. And now we look at our revenue every year. Our revenue is the amount of electricity we generate times the price that we choose. So if we choose if we want to lower the price to 0.1, watch revenue right here will get much smaller. So now the revenue is smaller by a factor of 2. Okay. So this is what you need to do, Isaac, and everyone else, is you need to go through this spreadsheet and say, what are my costs? Where did this come from? Oh, this is the operating cost. That's what I have to pay every year. And my balance is going to be, the amount of money I made minus the amount that I had to pay in my costs, right? And my balance, how much money I have in the bank, is how much money I had in the bank last year plus the change that I got this year, right? And so we continue to go through from year to year to look at how much money I have in the bank right now. And this graph is just the balance as a function of the year. So Isaac, how was that? Do you understand the model better now?
Yes, yes, yes.
Ah,
Thank you.
okay. That's what needed to happen. I'm sorry I didn't do that before. Okay. Now let me show you the most important thing right here about nuclear is let's lower our costs so we're competitive. All right. That's about as low as we can get. It will take 20 years to pay it off. And what do we have? We have me paying $10 billion to build it and then starting to get revenue the next year. Is that real? If I take out my money today to build a reactor, am I going to be selling electricity next year? How long do I have to wait? Yeah, probably 10 years, no revenue. So what happens if we for 10 years, wait, what just happened? Let me try this again. What happens if for 10 years there's no revenue? Right? Oh no. So what you see is I go deeper and deeper into debt, and it's exponential because I'm paying interest. And then after 10 years, I am so deep into debt that the interest on my debt is more than the money that I get. Right? So I lose. Oh no. So I've got to charge more money. That's not enough. How about 25 cents a kilowatt hour? Now we're okay. So now what we see is I go deeper and deeper into debt for 10 years. And now my revenue is enough to get me back out of debt. And now I'm happy after 40 years. And after 40 years, they close the plant. What do I say? No, don't close the plant. I've paid off the debt. I'm making a lot of money now. And I'm going to make more money if I keep going. And so that's the key to understanding this is, I can change all these parameters. And you can say, now I win, but I had to charge 25 cents a kilowatt hour for my electricity in order to pay off the debt. Okay. So, then you say, well, what if we had a modular nuclear reactor and it only took 4 years to pay off the debt? Then you're like, that's way better, right? Now I can lower the cost of electricity to just 20 cents per kilowatt hour, right? What if the interest rate is higher? What if it's 12%? Then you're like, oh no, then you lose again, right? Now you have to charge more money for your electricity. So, what if, the electricity goes down and you only have a 50% duty cycle? Oh, that's 50,000, Pete. No, that's not allowed. Yeah, then you lose too. Okay, so what I want from all of you is I want you to play with this model and think of all the things that can change. I want you to click on all of those cells and find out, what of these can I change and how do you calculate these different things? Glory. You have to mute your unmute.
Yes, I just wanted to understand on the figures on the costs. What does 1.00 E plus 10 mean?
Oh,
I
sorry.
think I'm lost. Yeah.
This is scientific notation. This is 1 times 10 to the 9th power, right up here, right? So this is your exponent. 9 is your exponent. This is how Excel does big numbers. Like if you look at this, this is 1 0, this is 1 billion. Do you see this up here? Glory?
Yes, I see it.
Okay, so you understand now, right?
Yeah, I
Yeah.
understand now.
And so this is, I mean, when you talk about money, this is $12.7 billion, right? I'm not going to write that out. We use it in scientific notation. Lonje.
Yes. I just wanted to ask if this model can work also for a solar.
Yes.
Maybe you want
Yes.
to integrate the solar
Yes.
system into the mini grid.
Totally, you should use this, right? So for solar, you'd have, you know, 1,000 watts for your house. Okay. Then you'd say the capital cost is how many dollars per watt? Oh, it's $0.5 per watt, right? And the duty cycle. Oh, right, the duty cycle for solar. Yeah, you're going to lose there. Maybe it's only 1/5 of the time, right? And now you can say, I mean, I didn't fill in all the ones. You'd have to go through there and look at them. But now we can lower this to, 10 cents a kilowatt hour. Okay, wait, why is it negative? Why are we losing? Oh,
Maybe operation
I
costs.
filled the wrong thing in. Let's see, this is $1 a kilowatt hour. Yeah, operations. Let's take a look at the annual operating cost. Where does it come from? Operations, dollars per. Oh, here we go. It's not going to cost us for our 1,000-watt system. It's not going to cost us millions of dollars a year, right? That's going to be 2, right? Now things are better. Right. Oh, and it won't take
Quite interesting.
3 years to build. It will put it up in 1 year, right? Well, probably even the first year, right? So yes, like I'm not saying I did a good job here. I'm just saying this is exactly what you can do. And already we can lower the price, 0.07. Yeah, if it's 7 cents a kilowatt hour, then it would take 20 years to pay off. But I just threw in some numbers, right? You have to be more careful about the numbers you put in. Great question. Yeah, and you should definitely use this and think about the different options we have in Malawi. All right. Great. So I went way over. It's 7:30. If you come earlier tomorrow,
Yeah.
we'll finish earlier tomorrow too. So this was great. I love the fact
Other
that I
question.
went into breakout rooms and you were all arguing about Malawi. That's great. Thanks so much. So class is over, and
I have a question.
I'm not leaving, but class is over. You're welcome to leave, and we'll just talk for a while. Okay? Thank you. James, what's up?
Yeah, do you think Malawi is ready for nuclear?
Friday.
And
We talk
if
about
we are
this.
not ready,
We talk about this Friday. You talk to your friends about it. You talk to your mom about it, right? Talk to everybody you know about it. And Friday, we're going to discuss it in class. Okay?
oh, that's not it.
What's that?
That is noted. I've taken note of what you have said.
Okay. Oh, that is noted. All right.
Yes.
Anyone else?
Hello.
Christina, what's up?
Yes. My question is, I understand you explained about the misconception that people have about nuclear.
Yes.
But then, in your country, how did you convince people to buy in the idea of nuclear?
Yeah.
I am thinking if we would like to do that in Malawi, there will be a lot of tension. So nuclear has a lot of bad news, but how can we convince people of the idea?
Yeah.
Yeah, that's my question.
That's great. Now, uh, you need to mobilize, right? It's going to start with young people like you. That's going to make the change, right? The pro-nuclear people, they got out and they started educating people, uh, and they got out in the street to protest. And it wasn't a violent protest. It wasn't like what's happening with Trump right now. It was just people saying, look, um, we need to make better decisions. But there's something else that happened, Christina. So I've been teaching this class for 20 years. Okay. When I started teaching the class, people were afraid of nuclear. My students were. They're not afraid of nuclear anymore. They're afraid of climate change. 20 years ago, climate change was a thing that, like, do you really believe in that crap? Climate change. But now, we see it everywhere. We can see it destroying the world. So it's not that we did anything in particular. It's that the world changed and people started seeing the facts. I mean, the education with respect to nuclear accidents and dangers was really important, right? When you put the numbers down, this is how many people have died from nuclear. This is how many people have died from coal or whatever. It makes it harder and harder to hate nuclear. So it's a long process. It took a long time. How was that?
Yeah, no, it makes sense. I think we're going to buy that.
Yeah.
Yeah, people, I think even myself, I need a lot of convincing that why should I choose nuclear over solar? Because I mean, when you go to a solar farm, even the way it looks is more safer than when I go to a nuclear generation plant. So I think when we engage a lot in this, yeah, I might change my mind. You have to do a lot of convincing, but yeah, it makes sense.
Yeah, I think the very first thing, Christina, is to educate yourself. And that's what we're doing. You want to learn the facts, you want to learn how people behave, and you want to make your choice. That's what we're doing. Thank you so much for your input.
Thank you.
Anyone else? Christina, if you're interested in nuts and bolts, right? Like, I'm not saying we should be nuclear, but if you want to promote nuclear, you can contact Heather.
Okay.
Okay. You have
Uh,
you have that information?
no, I do not.
Let me just check something here. I think I've written it down. I'm just looking here. She came to class 2, which was yesterday. Yeah, where did I put her information? Uh, I'll get that out, okay?
All right.
Yeah. So here's what I can give you. I keep a blog. So this is personal, but I'm glad to share it with the students. All right. Um, Let me just share my screen here. Okay. Now we go to my blog. See Pete's life here. All right. And this is my trip to Malawi the first time 3 years ago, but here I am now. Right. And this is my trip here, all the things that I do, right? My friends. Now, I bought a bicycle, I met all of these people. Um, yeah. And we want to go it was Tuesday, right? Monday, Tuesday. Here we go. Right. So here are some links you can follow, right? You can also see Heather. So I need to put Heather. Did I not put her email in here? No. So I'll put her email as well. But what I'll do now is I'll give you the link to my blog. Okay? Are you still
All
there?
right.
Yeah.
Yeah, I'm here.
I'm going to put it in the chat. All right. So you're welcome to read all about what I'm doing. I could give you all my blog anyway. And you can follow her there. But Pricey is a woman who runs Africa for Nuclear. So you can write to Heather, but if what you really want to do is work for nuclear in Africa, you meet this person.
All right.
You can see that, right?
Mm.
Great.